Okay, so the first section we're going to take a look at is 1.1. Okay, a lot of different topics in this section, mostly review. I think the only thing you'll find that's new is how you zoom in and out on a graphing calculator. Okay, so I'm going to show you a little bit about that, and that's the only thing we're going to do today on the calculator. So this is a basic number system diagram that you've seen probably since Algebra 1 that shows you all the different kinds of numbers that we work with, starting with the simplest numbers on the inside, counting, and working our way out to more and more complicated and more theoretical numbers. These are the numbers that you work with in Algebra 1. Okay, so I'm not going to write a definition on the board for every one of them, because you've seen or hopefully heard of all these before. But I'll describe them, and if there's anything you feel you need to write down as I say it, go ahead. So your counting numbers don't include any fractions or decimals. Just think about when you're counting things. You don't count like halves or quarters. You count 1, 2, 3, 4, 5. And also when you're counting, what number do you start with? Yeah, you start with 1. Counting numbers don't include 0. And the whole reason that we need more than just counting numbers is because if you start to think about certain kinds of arithmetic problems, like that's okay. If you add 3 plus 2, you get 5, and that's a counting number. The problem is, what if I did that? 3 is a counting number, 3 is a counting number, and I'm subtracting 2 counting numbers. But the answer that I get is not a counting number. So you've taken 2 counting numbers, you've done something to them, add, subtract, multiply, or divide, and the answer that you get is no longer something in the counting number system. So that's why we have whole numbers. So whole numbers give us 0. That's the only difference between counting numbers and whole numbers. Okay, so whole numbers include 0, and they allow you to do something minus itself. Okay, without 0, you can't do 3 minus 3. There wouldn't be an answer. But even including 0, we can still run into problems, not even thinking about division. Division has other things that can happen. But just basic subtraction. Can anybody think of a subtraction problem where you take an integer? You take a whole number minus a whole number, and you don't get a whole number. Anybody think of something you could do? So remember, whole numbers, they just include 0 and up. Yeah?
3 minus 5.
So 3 minus 5. Okay, if all you understand is whole numbers, like maybe somebody in kindergarten or first grade, and I said, okay, I want you to do 3 minus 5, they might look at that and say, well, you can never take away and have the bigger number after the smaller number, right? Because you can't take away more than you have. Well, you can. It's just you have to understand another kind of number to do that. And that's where integers come in. So integers now include all the numbers you had before, plus they include negative numbers. So like -3, -2, -1, 0, 1, 2, 3, 4. But even with integers, there's still basic arithmetic you could do that would run into a problem. It doesn't have to do with adding or subtracting or multiplying. Can anybody think of a problem where you take an integer, you do something to it, and all of a sudden the answer wouldn't be an integer anymore? Yeah? 1 divided by 2. Okay, again, if you only understand the concept of integers, up to integers, 1 divided by 2 is impossible. That's like taking one object and giving it to 2 people equally. Well, I can't. The only way I can do that is if I break it into pieces, right? Parts and fractions of a number. And that's where rational numbers come in. Okay, so rational numbers include everything you had before, positives, negatives, and zeros, but now they also include fractions and decimals. I think I wrote that one down. So that's a rational number. It's any number that can be written as a over b, where a and b are integers, like 2 over 3 or 7 over 13, whatever you want. The only thing the bottom number can't be is 0. And this is a number system that we also have a symbol for it. I'm going to show you guys what the symbols are after. But does anybody remember when you divide two numbers, what you call it? Like when you add two numbers, it's a sum. Yeah?
Quotient.
Quotient. And the symbol for rational numbers is a Q. So we'll talk about that in a second. So rational numbers pretty much include everything that you would need to do, I would say, everyday math. Okay? Most people that have to deal with numbers, that's as complicated as they would need. Maybe if you're cooking, you don't need 2 cups of flour or 3 cups. You need a fraction in there. Maybe you need 2.5 cups, right? When you pay for something out at the store, it might not be $11, might not be $12, might be $11 and 32 hundredths of the next dollar. That's a fraction of the next dollar. When we start to get beyond rational numbers, now we're getting more theoretical. Okay, numbers that people don't use as much in everyday life. So rational numbers include everything that you can write as a fraction. Irrational is everything you can't. Does anybody know a number that you can't write as a fraction? Yeah?
Square root of 5.
Yeah. It's numbers like square roots that aren't perfect squares. So I don't mean like square root 4, square root 9. That's different. But numbers that aren't perfect squares, you can't write as a fraction. And I can prove to you it's impossible. Like, you will never be able to write square root of 5 as a fraction. I don't care if you get more powerful computers or not, it's just never possible. Can never be done. Pi, as far as we know, that cannot be written as a fraction. So now, if you take all the numbers that you can write as fractions, all the numbers that you can't write as fractions, you put them all together, that's called the real number system. And that's what you study in Algebra 1, real numbers. Okay, beyond that, or another type of number we're not going to talk about right now. But yeah, we'll get into imaginary and complex later on. But that's what you study in Algebra 1. Okay, and the way this diagram works is if you're on the inside box, you're automatically part of the outer box. And the way you can think of it is like places. Okay? Think of counting numbers as Boston, whole numbers as Massachusetts, integers as New England, and rational numbers as the United States. Okay? Each number set gets bigger as you move up. If you're in Massachusetts, are you automatically in New England? Yeah. If you're in New England, are you automatically in Massachusetts? No, it doesn't work the other way. So if you're a whole number, you're automatically in the integers. But if you're an integer, it doesn't mean you're automatically in the whole number. And if you just think of it like places, that's how it works. Okay. So I told you I'd give you some symbols for some of the number sets. So rational, that one makes sense to me. Q for quotient. And a capital R for reals. They do have these kind of extra lines in them. That's how our book draws them.
To prevent confusion, right?
Yeah, so you don't think like maybe if you use like an R in a problem or even a capital R, you might think that's a variable. But when you draw it like that, we know it's not a variable. It's a symbol that represents real numbers. That Q represents rational, and the Z represents integers. I don't really know why they use Z for integers. So what if I did this? A little bit of an extension of that symbol, but what do you think a Q with a little plus sign would mean? I guess you could also put a minus sign there. Those are the only two symbols you could put there that really mean something. Yeah, Amaya?
Is it just that the number is positive?
Yeah, this would mean specifically positive rational numbers. And if you made it a negative, that means I'm talking about negative rational numbers. Is 0 positive or negative? Neither. Right. So 0 isn't positive or negative. It is even, but it's not positive or negative. Okay, everyone have those symbols? All right. So now we're going to talk about a few different operations and properties. In math, if an operation is binary, it means it takes two things to make it work. Whenever you do addition, subtraction, multiplication, and division, you need to have two numbers to perform that operation. I can't do 9 plus and hit enter. 9 plus what? Like, the calculator doesn't know what the other number is supposed to be. Okay? There are certain operations in math that don't need two numbers. Square root of 7. I don't need to put another number under the square root. I can just put a single number and the calculator knows what to do with it. But these 4 operations all require two numbers. So we're going to look at some different properties for addition. Some you might remember, some you might not. And a lot of these properties also apply to multiplication. Okay, but we're gonna look at them for addition, and for the multiplication ones, I'm going to refer you to a page in the book. Just to explain these properties to you, I'm going to need to use three variables. Okay, I'm going to use the variables a, b, and c. And I want you to think of a, b, and c as being any real number that you want. Remember, real numbers, positives, negatives, fractions, decimals, 0. Basically anything that's not imaginary. Okay, so real numbers are the biggest number set that I just talked about. Okay, the first property is called closure. So I just said earlier that A represents what kind of number? What kind of number does A represent? Yeah. A what?
A real number.
Yep. This is a real number. And what kind of number does B represent? Yeah. Another real number. And what I'm saying is that if you add a real number to a real number, the answer will always be a real number. It's impossible for it to not be. So the idea of closure means you started with a number in a certain box, you took another number from that same box, and the answer that you get is always in the box you started with. Okay? That's what closure means. Let me show you something that is not closure. Does everyone agree that 3 is a counting number? Okay. Does everyone agree that 6 is a counting number? Okay. Is the answer that I get when I do that a counting number? Sorry. What do you think? Not sure what I did. But yeah, no, it's not. So this is not an example of closure. You started with a counting number, you took another counting number, you did something to the 2, and the answer that you got is not in the type of number you started with. Okay? So subtraction, we would say that the subtraction property is not closed with counting numbers, because there is a way for you to start with 2 counting numbers, do a subtraction problem, and not get a counting number as the answer. Okay? So it's not closed. But with addition, in fact, addition, subtraction, multiplication, and division are all closed under the real number system. There's no way that you can take a real number, divide by a real number, and not get a real number. You always will. Okay? Another property is commutative. Probably a little more familiar. Commutative is when you think about commute. Like if you commute between here and in your house, I mean your job, means you go back and forth, you switch places. That's what happens with commutative property. You switch places with what you're adding. Okay. Associative doesn't have to do with switching the order. It's the same order, ABC, ABC, but think of like when you associate. Right? When you associate, you do that in a group. Like who you associate with is kind of like Who are your group of people that you talk to, right? So it's how you group things. And with addition, it doesn't matter if you add B plus C first or A plus B. You'll get the same thing. Next property is identity. So the identity property is something you can do with addition and get the same thing you started with back. What can you do in addition that would give you back the same thing you started with? Yeah.
Add 0.
Yeah, add 0. So that's the identity property for addition. Now, what would it be for multiplication? What can you do multiplication-wise and get back the same thing you started with? Let me try to learn some names. Yeah, Ben?
Would you multiply by 1?
Yeah, that would be multiplying by 1. Okay? So the properties for addition and multiplication are similar, but a little different depending whether you're adding or multiplying. Okay, the inverse property for addition is what you can do to a number to turn it into 0, and that would be to add its opposite. We think of inverses when we're solving equations. Okay, if I was going to solve that in Algebra 1, I'd say, all right, your first step is to get 3 on the other side, so you've got to do the inverse operation of plus 3, which is minus 3. Because we're trying to make that 3 on the left a 0 and put it on the other side and make it a 9. Okay, and distributive property. So if you have addition inside the parentheses, you can distribute what's on the outside. And what's on the outside could be before the parentheses or after. We usually put it before. That's how I do it. But that's the distributive property. Okay, and on page 2 in the book, they go through those same properties again for multiplication. There's no such thing as a distributive property for multiplication, though. Like if you had this, you don't distribute the 3 to the 4 and the 5, okay? Because it's multiplication. Only distributive property only applies with addition and subtraction inside parentheses. Any questions on that? All right. So let's do it this way. What I want to do is, I'm going to show you the name of property, and I want you to tell me how to do that property in this equation. Okay, so this is a problem where you would see on a test where I'm kind of asking you to identify how to do a certain property, or I might do the property for you and then ask you to tell me the name of what I did. Okay, I could do it either way. All right, so looking at that equation, which side has distributive property on it? The left or the right? Yeah, the left. And can you tell me, who said left? Yeah, Waylon, can you tell me how would you do the distributive property? You don't have to simplify it, that's going to be the next step. But just tell me what you would do to do the distributive property. 2 times x plus 2 times 3. Yep. So that is the distributive property. Now, most of you probably would have simplified that at the same time. I'm just really breaking it down. So 2x plus 6 equals 6 plus 2x. And now what we have on the left and the right, it's not exactly the same, but it's close. The property that allows us to, what did I say commutative property has to do with? The order or the grouping? Yeah.
The grouping?
So the grouping is associative. So commutative is the order. And that's the property that allows us to change the order you're adding two things. So that's the reason why you can change 2x plus 6 to 6 plus 2x. And basically that's a proof. Right? You did a set of steps and you justified each step with a reason. So you basically proved that these two equations, or you proved that these two expressions are exactly the same thing. Is there any question on that? Okay. Alright, so let's, oh, that's it for that. Okay, so next thing, not even a two-dimensional coordinate system, just one-dimensional, just a number line. So whenever we draw number lines, we need to make sure negatives go to the left, positives go to the right. If it was a vertical number line, negatives down, positives up. The center, or where you put the 0 mark, that's generally called the origin. And when we use a number line, now we can talk about the relationship of numbers to each other. And there's 4 symbols that you can use that describe how one number compares to another number on a number line. Does anybody know the names of the symbols I'm thinking of? Yeah?
Greater than,
Yeah.
less than, equal to?
Yeah, the greater thans, the less thans, and then greater than or equal to or less than or equal to. So these 4 symbols basically allow us to give an order to numbers and say that something is bigger or smaller. Okay? If you already know these symbols, I mean, you don't have to write them down. I'm just trying to make sure everybody knows what those 4 symbols are. And how about the name of all 4 of these symbols as a group? Begins with an I. What are all those symbols called? Yeah.
Inequality?
They're called inequality symbols. Yep. So a lot of times what we'll do is when we solve an inequality, we're going to graph it on a number line. Depending on whether you have a greater than or a less than, or greater than or equal to, less than or equal to, you're going to use a certain type of circle. If we have a greater than or less than, it's an open circle. Greater than or equal to, less than or equal to, closed circle. So you kind of think if you've got the little extra symbol underneath, then you have to take the extra step and fill in the circle. And then the last thing we have to do is shade. As long as you set it up so it's variable, symbol, and then the number, in that order, you can always shade in the direction that the inequality is pointing. If you set it up in that order, variable, inequality symbol, number. So let's look at an example. Okay. So which one of these is set up in the order I just said? The one on the left or the one on the right? About Dex.
The one on the left.
Yeah, these are the same thing. X is greater than or equal to 2, 2 is less than or equal to x. But that is the way we would generally prefer to write it. Okay? If you need to rewrite an inequality, you can just switch the letter and the number, but then you also need to switch the direction it's pointing. Okay. All right, so Nick, if I want to graph that, I have my number line. What kind of circle?
It'd be one that's filled in.
Yep, filled in, and it's going to be filled in on what number?
2.
It's going to be a filled in circle on the 2. And we want to shade everything that's greater than or equal to 2. So Holly, which way is greater than or equal to going to go?
To the right.
Yep, we're going to shade the direction it's pointing, which is to the right. That's it. So that's graphing an inequality on a number line. Any questions on that? Okay. Let's try this one. Lizzie, are these representing the same thing? Yeah. You've got a 3 and a y. You've got a 3 and a y. It's pointing at the y. It's pointing at the y. So yeah, they are the same thing. Which one would you think we prefer? The one on the left or the one on the right?
The one on the left,
How come?
because the first number is the one that's pointing towards, so the one on the right.
So we generally, if we want to go with the direction that the inequality symbol is pointing, okay, to tell us which way to shade, we always want to set it up in that order. So variable, then the inequality symbol, and then the number. So I would say this would probably be the way you'd see it more often, okay, like in the book and stuff like that. All right. Is it Everett? Yeah. What kind of circle do you need on this one? Open or closed?
Open.
Yeah, open circle. And what number would I put the open circle on? 3. So I'll make my number line. Open circle on 3. And Aiden, which way am I going to shade?
You're gonna shade to the left.
Yeah, everything that's less than 3. There you go. Any questions on that one? Okay. Now, there is another way that you can graph that instead of using a closed circle and an open circle. I don't care which method you use. You can use closed circle and open circle. I'm just letting you know in the book, you're going to see a little bit different symbol. Okay? Instead of a closed circle, our book uses a bracket. Okay? It's the same idea. Okay? When you have a greater than or equal to, or less than or equal to, the book is going to use a bracket. It's still going to be a bracket on the same number. But you got to think a little bit more about it because the bracket needs to face the way you're going to shade. So Michael, when we did x is greater than or equal to 2, which way did we shade?
To the right.
To the right. So the bracket that we're going to use is going to look like this. It's going to open to the right, and we're going to shade that way. Again, I don't care which way you do it, but I'm just letting you know you're going to see that in the book. Now, if the book uses a bracket for the greater than or equal to, less than or equal to, anybody have a guess what symbol they're going to use for greater than and less than? Yep.
They're like a parenthesis.
Yep, they're going to use a parenthesis. So instead of open and closed circle, the book used brackets and parentheses. Okay, so just like we did before, we do an open circle on the 3. If you're doing it the way the book's going to do it, we're going to do a parenthesis on the 3. And then shade to the left. And that's it. Just a different way of doing it. Most of you probably haven't seen that before, but you can do it that way. Questions on that? Okay. All right, absolute value. So one way to think of absolute value, very kind of visual way to think about it, is it's the distance from 0 on a number line. Now let's say I really wanted to break that down. Okay, so something like a computer could understand. If I had a positive number, what would I do to it to take the absolute value? If I had a number that was positive and I wanted you to give me the absolute value, yeah?
You would subtract from that? What do you mean?
So like if I gave you the number 5 and I said, explain to me what you need to do to that number to make it its absolute value.
You would want to subtract 5 from it, which would put it in the like bracket things with, I don't know what I'm saying.
All right, anyone have another thought? If you have a number that's positive and you want to take the absolute value of it, what do you need to do to it? Yeah?
Take the number that it is, like it was
Just
5.
take the number that it is. You don't have to do anything to it, yeah. So if you have a number that's already greater than or equal to 0, and you want to take the absolute value of it, just give me back the same number. You don't have to do anything to it. But what if you have a number that's not greater than or equal to 0? What would you have to do to a number to make it its absolute value if it wasn't greater than or equal to 0? Yeah?
Remove the negative sign from it.
Okay, and how could you do that mathematically? Think of like, add, subtract, multiply, or divide. What could you do to that number? Yeah?
Could you multiply by negative 1?
Exactly. If you have a number that's less than 0, that means it's negative, and you want to know the absolute value of it, you multiply it by negative 1. Okay, that's a really formal way of thinking of absolute value. You either give me back the same number, or you multiply your number by negative 1. One of those two things will always give you the absolute value. You give me back the same number in the top case, you multiply by negative 1 in the bottom case. But the big idea here is absolute value is always positive. That's what these rules will do for you. Well, positive or 0. So if I gave you just a simple couple absolute value problems, absolute value of 6 would be 6. That's the top case. Just give me back the same number. Absolute value of negative 3? 3. That's the bottom case. You've got to multiply that number by negative 1, and that turns it into its absolute value. Okay. Any questions on that? All right. So what we can use absolute value for is to find the distance between two numbers on a number line. And that's the formula. So distance between two numbers on a number line is absolute value of A minus B. Now, does the order matter? What do you think? Jack? No. Normally with subtraction, the order matters, but not if you do the absolute value, then the order doesn't matter. So you could do A minus B or B minus A. You'll get the same thing if you take the absolute value. Okay. So let's set this one up. I'm going to find the distance between negative 2 and negative 9. So Lucas, if I wanted to set this up, let's let negative 2 be A, let negative 9 be B, what would I put inside my bars?
You could put negative 2 minus negative 9, which simplifies to the absolute value of negative 2 plus 9.
Yep, so that becomes minus a minus, becomes plus 9. And Cecilia, we'll do what's inside these bars. What's negative 2 plus 9?
That would be 7.
7?
No, yeah, 7.
Yep, 7. And absolute value of 7 is 7. Okay. So a real simple example, just finding the distance between 2 points on a number line. Any questions on that? So again, we're doing a lot of different things today, but I'm hoping they're all kind of short, simple, quick things. All right, so we talked about a one-dimensional coordinate system. Now we're going to go into 2D. In a 2D coordinate system, you not only have one number line, you have two, a vertical and a horizontal. What do you normally call the vertical number line? I don't really call it a number line anymore. Everett?
X-axis.
X-axis. And what about the vertical number line? Yeah, Ben?
Y-axis.
The y-axis. And the x and the y-axis, they intersect at a point, and that point has a name. What do we call that, Bella?
Origin.
Origin. And when you draw your x and y-axis, it separates the coordinate plane into 4 regions. What do we call each one of those regions?
Quadrant.
Quadrants. That covers pretty much everything. Oh yeah, quadrants are numbered too. Quadrant 1 starts in the upper right, and they go counterclockwise. 1, 2, 3, 4. In quadrant 1, well, actually, if you want to get to a point in the coordinate plane, you use something like this to specify a location. What is this called? You have those two parentheses and numbers and a comma between them. Yeah. Yeah, it's a coordinate point. Specifically in 2D, we call it an ordered pair. In 3D, it's still a coordinate. We call it an ordered triple. So X is the horizontal movement. Y is the vertical. And again, just like you've always learned, positive is right and up. Negative is left and down. So I'm showing you in each quadrant what a coordinate would look like. Quadrant 1, both the X and the Y are positive, and so on. Okay, so any questions on the coordinate plane? Okay, Algebra 1, I spent a lot more time, but I'm just trying to go through it pretty quick. Okay. Oh, we're already at the calculator, I think. All right. So zooming on a calculator. So the reason zooming is important is because sometimes you need to see something that's off the screen. And zooming is something that you don't just get good at. It's just like saying, well, get good at hockey. Well, there's kind of a lot of things that have to happen for you to get, to be a good hockey player. Same thing with zooming. There's a lot of practice it takes to kind of figure out how you should zoom. Right? Just watch me type something in. And you don't have to type it. You could just watch me do it. Bless you. Okay, whenever I want to type something in the upper left, if you want to try typing it, I guess you can. It's up to you. But to turn the calculator on, you need to press on in the lower left. And if you want to get to a screen where you want to graph something, there's a Y equals button. Okay, it's all the way in the upper left. Okay, I'm going to press that Y equals button. If there's already something there, I want to clear it out because I'm going to type in my own thing. The clear button is on the right-hand side, and it's just below the directional arrows. So you can type in, I think, up to 9 or 10 things at once. There might be a Y0 at the bottom if you go down.
Yes.
Yeah. But you can type in a lot of different graphs. Okay, I'm going to type in something like this, x squared plus 10. What kind of graph is that? X squared plus 10. Like there's a name for that. Anybody remember what it's called? Well, there's a name for the kind of equation it is, and then there's a name of the shape you get when you draw it. Yep.
Is it called a quadratic equation?
That is a quadratic equation. Yep. And what's the shape you get when you graph a quadratic equation? What's that called? Yep. Parabola. All right. So parabola looks like a U shape. So let me press the zoom button. And a lot of times if I don't know where to start to set my window, the window is basically how high the X and Y axis go and how low the X and Y axis go. If I don't know where to start, I usually do zoom 6. Zoom 6 is what we call the standard window. And it's going to set your X axis from -10 to 10 and your Y axis -10 to 10. So that's the size graph paper you're going to have. So I'm going to hit zoom 6. There's my graph. If you see a little yellow circle in the upper right, that means it's thinking, it's doing something. And when it stops, it's done. So where's my parabola? Anybody know why I didn't get anything on the screen? Yeah?
Because the y-intercept was 10.
Yeah. Okay, we're going to talk more about transformations, but when you add a number onto the end of a function, that's a vertical shift. Okay, I shifted it up 10 units, which is off the screen. So what I'm going to do is I'm going to press the window button. It's right between Y equals and zoom. And I only need to change one of these numbers. It's either the X min, Y min, X max, or Y max. Anybody think they know which one I have to change so I can see it?
Y max.
Yeah. And a good value might be, you could try 20 for the Y max. Hit graph, and now you'll see a parabola. Okay, what you were looking at before was basically just that screen right there. It was shifted. So practicing zooming on the calculator to find where a graph is, it can be challenging. This one I just want you to watch me do. I'm going to type in x minus 5, x plus 3, and I'm going to type in x minus 9. Okay, if I were to FOIL and distribute all that out, that's a cubic equation. Okay, if I distributed it all out, because it has 3 factors in it. Now, if I do zoom 6, and I want to see what this graph looks like.
It's really big.
Okay, that's way off the screen. Okay, in general, I know that cubics can cross the x-axis 3 times. Okay, basically, the highest exponent tells you how many times it could cross. So it could look something like that. Could also look something like that. Might only cross once. But it's going to have that kind of shape to it. Could go the other way too. So it could come down and curve. But it's going to have a shape like that. Okay. So I know that when I'm looking for a certain kind of graph, I have a picture in my head of what it should look like. Well, I know it's going way up and it's going way down, but I don't know how high. So one thing that we're going to use to kind of help us is the table. Okay. If you, again, just watch me do this. I like to keep my calculator set up like that all year. When I go to table setup, that second window, I always put the x variable on ask and the y variable on auto. That's just how I keep mine set up all the time. And what that allows me to do is I can go to the graph and I can say, well, maybe it's around like 1 or 2. That might be where it's at its highest. So I want to see what happens when x is like 1 or 2. But I don't want to plug in a 1 or a 2 there. I just want the calculator to tell me, if x is 2, how high up am I? I'm trying to get an idea of how high up it goes. So if I press second table, I can type in 1, and I can see that I'm at 128 on the y-axis, and I can type in 2. Now I could have done that by just typing in 1 by hand here. 1 minus 5, 1 plus 3, and 1 minus 9, and then multiplied it all together. The table is a quicker way to do that. And now that I know this graph goes up to 128, I can use my window, and that gives me an idea. Maybe I'll try 150 and see if I can see the top of it now. Yep, now I can see the top of it. It's way up at 150. So that's better, but I still want to get an idea of how low this goes. Now, I can kind of tell just by looking at it, it doesn't go that much lower than the screen. So I'm at -10 right now, maybe -20, 30, 40, maybe like -60. And that's the process that I pretty much use when I'm trying to find a window that shows me my graph. It just takes a little practice to get used to doing it. Perfect. So now I can see how high it goes and how low it goes. But the point I'm trying to show you is sometimes it goes way off the screen. Okay? And it might not even just be up into the hundreds, it might go up into the thousands. Okay? We don't know. That's where the table is going to help us. We can just plug in any number we want, and it'll tell me what it comes out to when you plug that number in. Well, that's an interesting one, 90. So if I plug in 9 for x, I get 0 for y. What do you call a coordinate that has a y value of 0? Yeah? Let's go back here and look at the graph for a second. X-intercept, yeah. So 9 happens to be one of the x-intercepts. There's also 2 other ones, but 9 is one of them. Okay, that's all I wanted to show you for the calculator, just changing the zoom. We kind of already did that. I mean, I guess we can practice it one more time. When they give you 4 numbers and they say to set your calculator to that viewing rectangle. These are the x's, min, max, and the second two are always the y's, min, max. So in the homework, if a problem ever says find a viewing window or find a viewing rectangle that does something, there's no real work for you to show on paper other than just writing down what did you use for those four numbers on your calculator. The mins and the maxes for the x's and the y's. Domain, range. And if you want to practice doing that, you can. You just press the window button, type in -20 for the x min, hit enter, 20 for the x max. Don't worry about the x scale. The x scale is how often you see a tick mark on the screen. It doesn't really mean anything. You can set a tick mark every 5 minutes. I usually just leave it on 1. I never play with that. Yeah. Yep, you just sign it for me. And then ymin. Ymin. Let me make a mistake. And you scan the QR code up to the red light once you turn it to drink. Yeah. What mistake did I make there? Yeah?
The x and y value, or the y values are swapped for min and max.
Yeah, I swapped the min and max, so if I hit graph on that, it's going to give me some kind of error. Window range means you set a window that doesn't make sense. So you got to go back to your window, and you got to fix that and make it -20 to 20. Okay, you'll get different errors as you do this, and you'll kind of learn how to fix them, and I'll help you. Yeah. Okay, what's the error say? Does it say syntax? Okay, so that was the next thing I was going to mention. When you type in a negative number on here, there are 2 symbols for dashes. There's one below the 3, and then there's one over with the arithmetic buttons. The one below the 3 is how you do a negative. The one over by the multiply and divide is how you do subtraction. So if you type in a subtraction symbol and a 20, the calculator thinks there that you mean to do subtraction, something minus 20. If I hit graph, it's not. There we go. And I hit enter. It can't do that. Now, you could put a subtraction problem there. If you want to do 20, let's say you want to do 21 minus 1. You can do that, and then hit enter, and it'll change it to 20. But if you really want to put in a negative number, you've got to use the button below the 3. Okay? So negative number, subtraction problem. That's important. Again, don't worry about the scale. The scale just change how often you see tick marks. I never really worry about that. Okay, last thing. The last thing is the distance formula. So the distance formula basically, it's kind of like absolute value in 2D. It's giving you a distance between two things. Not necessarily the distance from the origin, but it's a distance. Because it's a distance, that means it's always going to be what kind of number? Yep.
Positive.
It's got to be positive, yep. Unless you're finding the distance between that point and that point, they're the same point, then it would be 0. But generally, it's not the same 2 points. So let's say that's P, and that's Q. You want to find the distance between those 2 points. Okay, the way we're going to do that is we're going to turn that into a shape. That's going to be one side of the shape. Does anybody have a thought what shape I'm going to turn that into?
Right triangle.
Yep, I'm going to turn that into a right triangle. And once I turn it into a right triangle, there's a theorem I can use to find the length of that side. First, does anybody have a guess in my right triangle what side that's going to be? Yeah? It's going to be my hypotenuse. I didn't draw that perfect. Let me just draw it by hand. So there's one side. There's the other side. So right triangle. So yep, PQ is going to be the hypotenuse. And does anybody remember the name of the theorem you can use to find the length of the hypotenuse if you know the other two sides? Yeah.
Pythagorean theorem.
Yeah, I'm going to use the Pythagorean theorem. And we're going to go back to a formula I showed you earlier. You've got a point here, and you've got a point here. You need to find the distance between these 2 points. That's the length of the bottom side of the triangle. Let me label this. P is x1, y1. And Q is x2, y2. x2, y2. So based on that, what's the coordinate right here? We have enough information to figure that out because we know this coordinate, which is at the same height as this one, and we know this coordinate, which is at the same vertical, well, distance over. Yeah.
Is it, y2 x1?
So x1 would be a point that lines up
Oh, okay.
somewhere.
Flipped,
Yeah, so what would the first one be? It would be x.
like x2
That's x2 because it's lined up with q,
and y1.
and it would be y1 because it's lined up with p. So now, how do you find the distance between this point and this point? You don't need the whole coordinate. You only need part of the coordinate for p and part of the coordinate that we just wrote down. What would be the distance from here to there? Yeah.
Subtract x1 from x2.
Yeah, or x2 minus x1, it doesn't really matter which way we do it, but yes, you need to subtract x2 minus x1. That'll give you the distance from here to here. So that's x2 minus x1. How about the distance from here to here? How would you get that one? Yeah,
That'd be y2 minus y.
it'd be y2 minus y1. So now you've got this distance, you've got this distance, just fill it into the Pythagorean theorem. Okay, so x, I think that's how you had said it first. x1 minus x2, that's the length of the bottom. y1 minus y2, that's the height. And to use that in the Pythagorean theorem, you have to square each one of them, add them together, and then take the square root. So the distance formula, it's really just thinking of the distance as a hypotenuse and using Pythagorean theorem. Let me just see. Oh, yeah, distance. All right, so let's fill in those numbers into our formula and then see what we got. What I like to do first is I just do kind of the template that I'm going to fill everything into. That way I don't forget the square root, squaring, adding, subtracting, all that stuff. Okay, how about Maddie? What could I plug? I actually have two choices, but what could I plug in for this first number right here? Could plug in 5. Oh, so yeah, we have, oh, yeah, 2 Maddies, sorry. So yeah, 5, and the other number I could use is 1. It doesn't matter which one you use. I'll just go with the first one you said. Okay, now that we picked 5, everything else has to be put in a certain spot. There are no more choices. So 5 goes here. Maddie, what's going to go right there? Yep, 1. So we have 5, 1. and then we're going to do 6, 4. Let's keep the order the same. All right. So Jet, 5 minus 1 is going to give me how much?
4.
4.
Square root of 16.
Square root is 16. And Clover, 6 minus 4 is going to give me
No, sorry, 2.
2. And then when you square that,
4.
you get 4. And I'm going to get square root of 20. Now, whenever we get a square root that we can simplify, we do need to break it down and simplify that. If you have a method that works for you, you can do it however you want. Okay, I'll show you how I do it. I try to think of 20 as the product of two numbers, one of them that I can take the square root of nicely in my head. How could you break up 20 into something times something, and one of them is a nice number you can take the square root of? Joe?
4 times 5.
Yeah.
Square root of 2, so you get 2 root 5.
You can break 20 up into 4 times 5, and then you can take the square root of each of those numbers separately. That's a property of square roots. And the square root of 4 you said was how much?
2 root 5.
Yep. So that's how you should write your final answer if you get a distance problem that has a square root that can be simplified. If you had something like square root of 23, well, you'd have been done. Nothing you could do to simplify that. Any question on that? All right, so last formula. The last formula is how you find not the distance between 2 points, but the halfway point. Think of like if you had 2 grades on a test, and I wanted to know, I don't usually call it this, but what if I wanted to find the halfway point between like a 75 and a 100? What do you call that when you can take 2 numbers and kind of find their halfway point? Remember what that's called? Yeah? It's the average. And that's exactly what the midpoint formula is. Okay. Taking these same 2 coordinates, if you want to know the point that's exactly halfway between them, you average them. And how do you average a coordinate? You average the x with the x and the y with the y. So to average the x's, there's 2 things you have to do. If you want to average 2 numbers, what's the first thing you do? Yeah?
Add them together.
Add them together. And then the last thing you do?
Divide by the
And in this case, you divide by
2.
2. Yep. So that's the midpoint formula. It's the average of the x's and the average of the y's. All right, so we'll finish up by finding the midpoint between -5, 2 and 3, 7. What's the average of the x values of those 2 coordinates? Yeah.
-5 plus 3 is 2 divided by 2 is 1.
Did you say that one more time? What's -5 plus 3?
-2 divided by 2 is -1.
-1. Yeah. So your x's average out to -1. And what do your y's average out to? Well, yeah, go ahead.
9 over 2.
9 over 2. Sure, you could say 9 over 2. You could say 4.5. Either way. Yep. Okay, so midpoint formula is a little easier than distance because you never have to deal with a square root. All right, it's a lot of different things we covered. Okay, all kinds of different things. Probably would have been like 3 or 4 lessons in Algebra 1. I'm hoping everything was pretty much review except maybe zooming on a calculator. But any questions on anything we did? Okay. So the homework is on the board, so it's page 11. Remember to find that, you'll go to Schoology. You can either download the entire book, chapter by chapter, or if you go to the 1.1 folder, you'll see the PDF just for that for tonight. So it's 1 through 16, 20 to 23, 30 to 32, 38, and 44. Sometimes I'll write odd or even. If I don't write anything, then it's just all. Okay, so tomorrow, first thing you come in, I'll check that. Hopefully we'll get a system where I can kind of check it pretty quick. We'll go over it, and then we'll do our last, it'll be our last lesson for the week. We don't have a test tomorrow.